right, so this is Campus Collaboration Showcase. So I'm up here. I'm going to be sharing the stage with a campus collaborator, Franz Franchetti from the ECE department. I briefed this project last year. It's automated code generation for high-performance, future-compatible graph libraries. It's a mouthful. It's in its second year. Technically the last year under this title, but it is an ongoing research project. I have multiple campus collaborators in the ECE department, including James Ho and Zemeng Lo. So yeah, this is a 2-year project. I'm in the second year, but it's really part of a long-term sustained investment by the SEI in this space, specifically graph analytics up to this point, going back to about 2013, 2012 timeframe. But it is transitioning to include machine learning and artificial intelligence. It has, over the years, included collaborators from the other national labs, especially Lincoln Labs, and more recently the Department of Energy PNNL, Pacific Northwest National Lab. It has resulted in customer engagements in the area of predictive analytics, pattern of life graph analytics, and projects similar to that. I'm not going to go into the detail in this slide. There are a couple of phrases that I use. It's we're developing graph algorithms for high performance. We use the phrase performance portable because if we can automate the generation of code targeted to specific platforms, and we can teach that technology about hardware capability of these platforms, we can write code once and generate code for any platform, in an ideal world. So that's our goal. Write once, run anywhere, fast. That's performance portability. But in addition to that, we want to be able to target future architectures. So things that are being developed under DARPA programs like Hive and SDH. And so that is future compatibility. So that is our long-term goal for this body of work. I don't need to motivate this too hard. Graphs are pervasive. They show up in our data all over the place, especially in areas that are relevant to the DoD, in ISR, social network analysis, and cybersecurity. About the only difference on this slide from last year to this year is the graphs are getting larger. We can't handle the graph size that we had last year, and so we down select, we filter out, we look at what we think is relevant and try and fit it into the machines that we have in the time that we need to compute it. The problem with graph algorithms are that as you're traversing the graph and looking for interesting parts, we're stressing the memory systems of these hardware architectures. Graphs aren't nice to that. They have unpredictable, irregular memory accesses. These hardware systems were developed for large-scale scientific codes in general. We have cache hierarchies that do, that hope for regular memory accesses that they can predict and preload before you need them. Graphs aren't like that. And so if you want to get high performance on these hardware platforms that we have today, you have to expend a tremendous amount of energy. You have to be an expert not only in the graph algorithms, but now you have to be an expert in the hardware platform, and more likely, you have to be an expert in the specific platform that you have. If you get a tech refresh and you get a new platform with different memory hierarchy, it's a pretty expensive and time-consuming process to get performance on these systems again. And so what before we get to the next slide, hardware is a moving target. We're getting new multi-core processors with different cache hierarchy behaviors. Many core processors in the Xeon Phi are coming online. We have accelerators like the GPU, and if we could get a TPU, we'd have those too. And they're being put into all of our processing, from cell phones to supercomputers. How do you use these? How do you leverage these to the maximum possible to get high performance in data-intensive computation? And what we really want is a separation of concerns first. So step one, separate the need to be an expert in two areas. Allow the graph analytics experts to develop algorithms without having to be experts in the hardware. And then allow those that are experts, especially in the hardware vendor companies, to produce software libraries that perform very well on their systems. We call that the separation of concerns. Last year, May of 2017, we released a graph programming specification. We call it GraphBLAS. BLAS stands for Basic Linear Algebra Subprograms. That harkens back to the 70s when the scientific community came out with a few primitive operations that they always use in their codes. We've come out as a community, researchers across government, academia, and industry, identifying primitives that you can develop quite a few graph algorithms from. And so the goal is give that API to the graph analytics experts, allow them to program codes against that API, and then get the hardware vendors or other experts in academia and industry and government to write the finely tuned primitive operations for different hardware architectures. If we can get the libraries for the hardware architectures, then we can write once and run anywhere, and we can run fast. So that was released May of 2017. It is a dozen primitive operations. They use sparse matrices to represent graphs. So this is basically linear algebra on sparse matrices. It's kind of like what scientific computing did with dense matrices. It's a little more complicated because the sparse matrix data structures are where the irregular memory access meets the hardware. And so there's a lot of work that would need to be done for that particular aspect. That was last year. So what's happened in 1 year? It's really quite amazing what's happened. We did another couple of releases of the API, and mainly driven by the development of implementations at a couple of different places. They found problems with the spec wording, a couple of minor errors in different operations. But we have a reference implementation out of the Power Systems Concept Group at IBM. So they have a full conformant library that performs the correct operations. It's not focused on performance right now, but it's kind of exciting that the Advanced Power Systems Concept Research Group at IBM is looking at this and maybe influencing the direction of future architectures. The work at Texas A&M is by Tim Davis. It is, he's a prodigious coder. He's written tons of lines of code for his GraphBLAS implementation. The interesting thing is, if you use MATLAB and you use sparse matrices, you use his code already. He is translating his experiences in developing code for MATLAB into a graph library, or GraphBLAS library, that is focused on performance. Here at Carnegie Mellon, we had the GraphBLAS template library. We released it in 2015. It was actually a proof of concept that helped develop the specification. We released again this year with a functionally equivalent version of the GraphBLAS library, but for C++. So the previous two libraries were in the C language. We have a version in C++, and that's produced a proposal for a C++ API. We've done that in collaboration with researchers who are now at PNNL that were at Indiana University a number of years ago. On the hardware front, so the previous libraries were focused on a normal single CPU system, single core. We're pushing into the accelerator space. One of my collaborators from UC Davis works with John Owens at that university. They have a Gunrock library that accelerates computations like this. They're converting or putting a layer on top of their library to be conformant with GraphBLAS, so you should be able to leverage GPUs within the next year or two. We here at CMU have been engaged by a government agency to try and port the GBTL implementation onto a special computer called the EMU Chick. That's all the back end, what I call the back end code. Now on the front end, on the other side of the API, all of this effort on the right, if anything, has shown us that the API is surprisingly complex. Testing it appropriately is extremely hard, and in fact, Tim Davis's code base is about 65% testing code. And he doesn't test it exhaustively. He actually has two modes. You can run about 100,000 or 1 million tests and it take a couple of days and test most of the API. Or you can turn a switch if you have a couple of weeks to test the API. IBM GraphBLAS, the IBM GraphBLAS effort asked us, do you have some testing code for us and things like that. So in GBTL, I hand wrote about 1,000 tests and then gave up and engaged another member of our group, Dr. Jason Larkin, on doing automated test generation for this API. I think one of the statistics is just for one operation, and we have 30 or 40 of them, to do exhaustive testing without regard to the data structure, the sparse matrix data structure, takes about 5 million tests to do exhaustive. If you include different data structures for acceleration on hardware architectures, it can easily grow into the hundreds of billions of tests in order to test exhaustively. So Dr. Larkin has pulled something out of NIST, a technology out of NIST called automated combinatorial testing for software, so the ACTS technology. It basically looks, or you tell it the characteristics of your operations, and it can generate, through combinatorial methods, a much reduced set of tests that will guarantee a certain level of code coverage. So we can drop 100 billion tests down to about 100,000 and get about the same coverage. And so this is automated test generation. We have plans to open source not only the tool to generate the tests, but the tests that were generated. So we're going to actually open source 2 things. For those who want to just run the tests on their implementations, they'll have that. For those who want to actually dig in, like Tim Davis will, to actually make sure that it is able to test the different data structures that he's putting in to optimize. So that's really exciting. In a collaboration with the University of Washington and folks at PNNL, joint appointments, we are putting Python wrappers on top of GBTL. And the goal there is to be able to embed accelerated GraphBLAS operations in data analytics pipelines that already use SciPy and NumPy and scikit-learn, whatever you're using. And then the last part, we've been developing a graph algorithms library as kind of driver applications for doing the other part of the work that Franz will be talking about in a minute. We have a library of graph algorithms basically proving that we can do this with GraphBLAS. We're up to about 30 algorithms and growing. But the really interesting thing, I only found out about 2 weeks ago at a IEEE conference in Boston, is that a researcher inside of Redis is using GraphBLAS to develop a graph query system for a NoSQL database that they're developing in-house. So we're already starting to see quite an acceleration of interest. I don't know where we are on the hype cycle, probably up near the peak somewhere. But the other half of our research project is addressing this problem. Implementations on the right-hand side still take a team of engineers that understand their hardware architecture extremely well to tune the primitives that we've specified. It's time-consuming, therefore it's costly, and it's just difficult. So what we're trying to get to is a tool that can understand the GraphBLAS API, that can understand the hardware, and map the primitives to any hardware architecture. And we're leveraging a tool out of CMU called Spiral, and I'm going to turn it over to Professor Franz Franchetti from the EC department, who's going to talk to you about the efforts on this area.
Thank you, Scott. And it's always my pleasure to be here at the ASCI review meeting, and let's see if I can make that work. Probably not. It's always the big things that fail, right? So thank you for having me here on stage, sharing the stage with Scott. And so what I'm going to talk about is the second aspect. So you saw in Scott's slides at the beginning that the hardware platforms that we're faced with today is just crazy. So the power envelope can go from a couple of watt or even milliwatt to hundreds of megawatts. It can go from single little embedded processor to 10,000s, 100,000s of cores chained together. And the architectures you're faced with is anything from CPU, GPU, FPGA, emuchiks, and I don't know what, and whatever DARPA is funding right now and whatever industry is building and not telling us about. And so about 20 years ago, the Spiral project started when Lou Auslander, Manuela Veloso, and Jose Mura were sharing a cab ride to the Pittsburgh airport, and they said, why don't we automate FFT generation? It was about 20 years ago. We just, it was in 98. And out of that idea grew the Spiral project that has been a very, very big project over the years on the campus. And the basic idea in the Spiral system is that traditionally you would have your math books, and then you would have a couple of people, applied mathematicians, computer scientists, computer engineers, compiler people, performance engineers, and they would then write a high-performance library like the FFTW, the BLAS, or GraphBLAS now, and then you hand that over to the less skilled programmers or the more productive programmers, and they then use that and just run with it because they know that the library is really efficient. The idea now is, well, instead of having all the experts shuffle assembly instructions for every new machine that comes out, have them do something better like develop a GraphBLAS API and the backend operations automate them. That was the idea of Spiral, but the key thing is that if the system does not produce the same performance as what the humans can do, nobody would accept it because there have been plenty of high-level systems that would not give you high performance. And so, given that, we really strived very hard to get to high performance. And initially, everything was based on FFTs. And the idea was that back in 92, I think, there was the Charles Van Loan book, which basically put a formal framework around the FFTs that people have informally been using, and he wrote the definitive book of how to write FFTs with matrices. And that gave rise to our formal framework. And now what happened is that Jeremy Kepner over at Lincoln Lab wrote a book like that about graph algorithms. And so we thought, let's jump at that. And after 3 students and having failed later, I said, maybe let's not jump at it. And then I met Scott, and he actually understood what it is. And out of that grew this collaboration that we could not figure it out, but he knew how to do that. And we started talking and eventually said, well, if you can explain to us how that actually works, then we can get it into Spiral and we can maybe solve the problem. And so the idea now is that you have an algorithm space and you have an architecture space. And abstractly, what you got to do is you got to pick an architecture, and then you have to search the algorithm space to find what algorithm fits nicely on the architecture. And usually a human has to do that because nobody understands architectures and algorithms well enough to actually automate that really well. So now the idea is if you can actually automate that, and if you capture algorithms and capture architecture and capture program transformations, then you can automate it. And so the GraphBLAS math behind it, the thing that Jeremy wrote and then that Scott formalized and wrote up in the GraphBLAS API, is the enabling step that we have a handle now on the graph algorithm space, a formal handle. We had already a formal handle on the architecture space and the program transformation space. And now we can impose the GraphBLAS API onto the hardware and say, dear computer, find us something that works well and implements a triangle counting on a GPU or something like that. So that's the basic idea. And you see here is search and here is pick a point. And 10 years ago, in a DARPA project, DESA, we started asking also the question, what if we basically want to search here and search here at the same time? Can we do co-optimization, hardware-software co-optimization and co-design? And the answer is yes, but for what we're doing for graphs, we're not quite there yet. So the enabling step to make all of that possible is basically that summary out of Scott's paper that describes, here is the operation in GraphBLAS, and here's the math, using the semi-ring and formalism that Jeremy Kepner and John Gilbert and everybody came up with. But now somebody had to translate that one for us in a way that we understand it and how to use algorithms. And so you see all these dots with circles, and so these are mathematical structures. They need to be properly defined. It's a long slog from, hey, this is the idea, to here's the actual specification. And so Scott went through that, and then we had it. And now that we have that, we basically can go and do what good algorithm designers do. You go to the whiteboard. On the whiteboard, you draw the problem and draw the solution, and you write the math that goes from problem to solution. Then you pick a simple, non-trivial example, and you work it out, and then eventually you write the program. So that's what you usually do. But it turns out that as you do that, you can also figure out that the actual specification of the problem is a mathematical statement, like the number of triangles is the sixth of the trace of the cube of the adjacency matrix. And somebody has to tell me that, because I wouldn't come up with that. That's a lot of theory and papers. But now, the other thing is that actually the algorithm, you would never run that, because you would not cube a sparse matrix. So the actual thing you do is you compute that expression, which means you do the product of the lower triangular matrix and its transpose over the semi-ring, and after that you compute the one norm, and then yada, yada, yada. And so that's kind of like what you do on the whiteboard. And when Scott comes over and we have a group meeting and we have a pizza and we talk about it and the students are in the room. And after we have that, Scott can write that program. And now that's a GraphBLAS program. But we now can say, hey, that's not a program, that's a specification. Because there's no side effects anywhere, there's really just math, and we can stick it into our system that has a formal system behind it. So the question is now, how do we stick it in? Well, my student Paul, who yesterday at the poster session had a poster about that, spent a year on really trying to understand all the nitty-gritty details to really get it in, and now we have the formal aspects of it in. And the formal aspects are actually pretty daunting, because it's a 20-year project in a 1980s computer algebra system that does anything from logic programming, constraint solving, to functional programming, and so forth. And so that we have this formalism that has operator notation, basic operations that are kind of like functional language, loop abstractions that are mathematics, and a rule-based compiler. And it's a huge, huge, huge rule system. How I usually explain it, it's similar to when you learn about integration. There's this huge rule system that explains to you how to integrate symbolically a function. And in high school you learn a little bit, and then you learn something and eventually use Mathematica. And Mathematica has all the books of integration coded up and applies it. And you're not guaranteed to succeed, right? Mathematica sometimes says, don't know how to integrate, it's a Bessel function or whatever. And so the same thing happens here just for code generation and for performance tuning and not for integration. But it's the same idea, and that's why it took us 20 years to get here. And now, but once you have it in there, you unlock, you have basically the magic key. And what you do is, we have now auto-tuning in a constraint space. Basically, the solution of the problem forms a complicated space of all the solutions. And now in that complicated space of all the solutions that comes from a problem and a hardware, You find all the good ones that actually implement the problem, and you can traverse them, and you have a special purpose compiler to implement them automatically. You have the formal approach to co-optimization, so you basically have now a squiggly line here and a squiggly line here, and you can attack the question, what's the right hardware for the software, what's the right software for the hardware, what's the right joint solution. Once you can do that, you can do architecture algorithm co-optimization, where you say, find me the argmin of a cost function that involves the algorithm and the hardware. Go off and do that optimization for me. And the latest addition to that is in the DARPA BRASS project, where we said, instead of a performance tuning program that basically runs offline at the beginning of installation time, turn it into a just-in-time compiler, a hotspot compiler, that when you run a program, you do inspector executor, you run it once for figuring out what's actually going on, then you run in the back end a lot of stuff, and then it comes back, and then in the execution mode, you just run really fast because you invoke the just-in-time compiler. And we are building that in a way that's future compatible, that you can plug in any kind of hardware description that we haven't thought about yet. And just yesterday in Matt Gaston's office, we talked about how maybe the EMU chip might be a nice next target here. So yeah, so that's basically what's happening here. And the DOE uses it for exascale FFTs, and so it's basically going somewhere. And what you saw yesterday in the poster session is my student Paul, who has been mainly working on that. After he went through all these step-by-step getting into the formalism, he can do a problem specification, which is basically just triangle count. Does not look very impressive, but there's a lot of math behind it. Then an algorithm has been chosen. That's now one of these breakdown rules, and it happens to be vector matrix vector multiplication with a nested accumulation, which is out of a paper that Zhemeng Lo developed with his students over the last couple of years to use his flame approach, how to do that. And then eventually it derives some loop invariant, and then some code comes out, and that's a high-level specification of the code using the math, which then eventually becomes abstract code, which is an internal representation, and after everything is done, final C code comes out and runs, and then in an afternoon, Paul added a parallelization OpenMP to it by just set a couple of flags. So that's kind of like the end of the project in a way that we but the starting point for the next project, where we basically showed, yeah, it can be done. Now Scott has this library of 30 algorithms. Now let's get all these algorithms in and see what we can do. And so it works. So you see just basically the screenshot of some internal code representation that doesn't really mean something to you, and some C code that means a little bit more to you probably, but still not a lot. So basically the system basically says, okay, go do it, and then the code comes out, and it basically writes for you the code instead of you having to write it. And again, remember, we're going towards a just-in-time compiler, that you write a GraphBLAS program, and as the GraphBLAS program runs, it invokes the system, and when it comes back, this one gets just linked as a shared object in the backend, and the user never ever knew it didn't call a library, but all of that stuff happened in the background. So we do have a pipeline going on in our research group. We have some people that are working on the specification and math part, some people on the implementation in the system, and some people looking at the next generation hardware. And my student Fazl Sadi, co-advised with Larry Pileggi, doing a chip design in ECE. He is looking at ASICs and FPGAs and algorithms. How would you do something like PageRank right there? And it turns out what you have to do is you have to go back to what you've learned in the supercomputing era. How do you do matrix vector on a big parallel machine? Take these algorithms and stick them on shrink them down basically on a single chip, because that's the right algorithm. And so we try out these things like a PageRank on the FPGA and the ASIC, and we just fabbed a chip, and it's coming back soon, and we have results on the Stratix 10, and this is also tied into IARPA projects where they need examples of give me some complicated chip designs that somebody has to then reverse engineer. And so we are leveraging that sometimes, and so we got all of that, and the idea really is you would write multiple iterations because PageRank iterates over the data multiple times. You basically have to fuse iterations across, basically fuse across iterations, and then you get reuse, and then suddenly the magic works. And the result is something on the order of between 20 and 100x. And we had that at this conference that Scott was talking about like 2 weeks ago. And as I walk to coffee and I come back, I see Dr. Rich Lindemann talking to my student, being excited by the 90x, and said, you guys need to do more of that. So we're happy to do so. So the other big thing, and this is really kind of like for joint working with SCI for us really exciting, is that after 20 years, we have decided to open source the Spiral system. The idea being there is a company that maintains it, like Red Hat does for Linux, so that if a defense contractor or government needs help, there's somebody to call and they don't have to all come to a professor and grad students. But it has a non-viral license, and the initial version is going on, and the GraphBLAS work we're doing here will all feed into that. So it's there. We are working on documentation. DOE is using it. We are using it in DoD. The Massachusetts SuperCloud will have it installed. We have it kind of like trying to push it out after 20 years. And we're looking forward with the SCI partnership to really help get that tool that's at least 5 big DARPA projects. It's like tens of millions of dollars over the 20 years was invested in it. And now SCI is enabling us to push it out, basically. This is a great, great thing to do that together. And so that's the point where I'm handing back to Scott.
Yep. So, like I said, this is an ongoing project. We've only touched the surface on graphs. It turns out that the sparse computations in graphs also apply to many areas in machine learning and AI. So for the next 3 years, we will be folding all of that study into this work. The GraphBLAS API group is on a hiatus, so we're taking time to allow people to implement before we come out with version 2. For FY19 and even beyond the next 3 years, is we really want to get into co-design and co-synthesis. So for the next 3 years, we'll also be building in some of the cost functions that include cost, size, weight, and power targets for your hardware platforms. But really, we want to get to full co-synthesis. When you give us the math, the algorithms that you want to run, and it proposes hardware for you, all the way down to, this is the ASIC that you want to design or produce. And so with that, I'll invite Franz back out, and we're happy to take some questions.
Sorry, I didn't mean to keep asking the first question, but is this, can I just get a container for this and drop it on my favorite cloud instance and make it work, or how far away from that are you? Or
a container with all of Spiral?
Yeah.
So that's a good question. So if you want to do FFTs, then we're pretty close to that because we've been working on it for a long time. And we're actually building kind of like, right now is a tarball, it's going to be a Git, and then the container is the next thing. Now, for graphs, it's an ongoing research project, so we'll have a first version of that in a container soon-ish, which means like the mystical year or something like that. So it's not quite there that you just get a container, but it's really, our goal is to get it out. And so if you have a particular use case, let us know, and we are looking for early adopters. We may have to say, look, this is still too far research out, so we can't quite do it yet. But if it's close enough, then it's a thing where we're really looking for early adopters.
And if you're interested in just trying out GraphBLAS itself, GraphBLAS is part of the Sweet Sparse library, which is also part of many Linux distributions today. So,
and let me just sort of try to frame the use of, like, okay, imagine you gave me the container and it had everything in it, right? And I was just able to deploy it and use it on demand. So where is your kind of sweet spot, right? Because at one extreme, you have the MATLAB world that will deploy stuff and push it onto FPGAs and do whatever they're going to do. And then you got the other side, we got Wolfram Alpha and company doing like their, I'll solve your differential equation for you and, whatever. And then down the middle, you have the graph processing world. So are you kind of that intermediate realm? I don't know if that is an intermediate realm, but, in that realm that neither of those two things do. It's kind of an interactive language of the mathematics of graph processing that, I can just call up eventually on the cloud and just make it work. Is that sort of the objective?
Yes.
Okay.
I think we're trying to be a lot of things, and it's with the help of industry and many other universities and other labs. I mean, we have Python efforts trying to make it available to the masses. We have folks that actually write MATLAB, the MATLAB backend, and I can imagine that this could fold into MATLAB in the future. When we're talking about, optimization for hardware, then we're getting into, the stratosphere of, power users, right?
Yeah, and so the idea there really is you want to have an API for the user that basically they can write their stuff against it and not knowing what's happening necessarily underneath. So basically you have an abstract API like the GraphBLAS. And then you either run against a reference implementation or a great library or against a system like Spiral where you basically have a just-in-time compiler, dynamic translation, grabbing your problem and your hardware and then doing as much as you can. And depending on whether you're basically in the pipeline just trying out as a data scientist and it doesn't really matter because you're just trying it out, or you're ready for production. And so David Padua out of UIUC once said, if you are running on an exascale machine, use a petascale machine to compile. And so that's kind of like the idea here. If you run something on a 12 terabyte machine for days on the Pittsburgh Supercomputing Center, then why don't you spend just a couple of hours on the 3 terabyte machine to make it run really fast and save like days on that big machine? And so depending on where on immediately return versus big job you are, you may or may not want to use a technology like that. But the user shouldn't see it, right? The user should just always write the same thing and then the magic happens, hopefully.
Thanks.
Anybody else?
All right.
Thank you very much.
Thanks again.
Thanks.